Hi there. So the main topic of today is to do a worked example of the Adams-Bashforth method, Adams-Bashforth 2, second order method. You can't beat sometimes just going through by hand, doing a few steps of the method to really get a feel for how it works. And we're going to repeat the example we did with the midpoint method one or two videos ago, so that we can sort of compare and contrast how it works, and also it should deliver a similar accuracy to the midpoint Runge-Kutta method. And we'll be able to see that. Okay. And then finally we'll finish off with just stating what the third order Adams-Bashforth method is, because that's a very commonly used method as well. Okay. Okay. So let's recap what we did last time. We derived a multi-step method. And by multi-step, I mean that we evaluate the function actually on the time step. And the name of it was Adams-Bashforth. Second order accurate AB2. And we integrated over a straight line approximation to the function, and the result we got was this, that xn plus 1 minus x of n equals delta t on 2, 3 times f of n minus f of n minus 1. So you can see clearly that this multi-step, because the function is evaluated exactly on the time steps. Actually, I just want to just go into this notation f of n. It's very compact, but actually that means f of x of n and t of n. But why can we do that? Let's just talk about that just on one board. So f of n is shorthand for f of x of n and t of n. So why can we do that? Well, x is a function of t. So f of x of t can be also written equals f of x as a function of t and t, so that in that sense any certain time t can determine both these variables. It's just purely a function of t. And when we discretize, so we have t goes to t of n, yeah, which is simply your integer times your time step. Okay. So that means that f of x of t comma t simply goes to f of x of t of n t of n. So this may be laborious if you've already got this already, but I thought I'd just make it clear why we can just use this shorthand. So basically n defines, because we've got n there and we've got n there, defines each value of n, value of f. So we can use the shorthand f of n, and that makes writing down the algebra a whole lot easier. Okay, but that's just a little bit of why we can do that. It's all because x is actually is intrinsically a function of t. So what we're going to do is we're going to return to our dx by dt equals 2t minus x. And we recall that we had a true solution of this was that x star at t equals 1 was simply e to the minus 1. Okay, so So that's our function f of x of t. So we're just going to return to that. And remember, we've evaluated the true solution, of course, so we evaluated it for Runge-Kutta. So we just get a comparison about how this accuracy compares to Runge-Kutta 2. It should be similar if they're both second order. The other thing is we just get a little, by doing one step, we get a feel practically as well as sort of theoretically about how this method works. Okay, so we're going to repeat this problem for AB2 now, which is our Allen-Bachelor 2. Now the first thing you may have noticed that we needed the function at n and n minus 1. So we need to generate those extra 2 initial starting points. So we need to actually start the problem off with forward Euler to generate n and n minus 1, and then we can proceed with AB2. So we start with, and you'll find this with the leapfrog as well. So that is simply that x1, the first one is x0 plus delta t times f of x 0, 0. And remember, in this problem we said x0 is minus 1. That's what we did before. And delta t was 0.1 and f0 was 1. So that's just using the results from before. So we've got 0.9. So the main thing is we're just seeing how this works. And once we've got now we have x0 and x1 defined, we can use our AB2. And maybe that's a slight drawback then of a multi-step method, maybe of a Runge-Kutta, is that we have to generate these initial conditions normally with a different method, maybe one with less accuracy than one we're trying to do. So in this case we're using a first order method to get the first 2. So obviously if you're using further and further back, then you know, it's getting it going, getting started is maybe a slight drawback. But so AB2 then is we then use, but once we've got those values, the formula is simple and simpler than Runge-Kutta. We do delta t on 2 times 3 of f1 minus f0. F1, which is the same, remember it's shorthand for f of x of 1 and t of 1. In fact, I'm going to just go on to the next board for this. Let me just write that out from the beginning, so we've got to use the whole board. So x2 is x1 plus delta t on 2, 3 of f1 minus f0. And then we need to evaluate these two pieces. F1, which equals f of x of 1, or t of 1, is f of x of 1, and of course t1, since time starts at t at 0, t1 is simply delta t, yeah? And remember f equals 2t minus x. I'll just put that up in the corner there. A few references, so it's 2 times t something. So that's equal to 2 times t, which is 2 delta t minus x1, and x1 was evaluated on the previous slide as 0.9. So know that from the forward Euler. So that is equal to 2 times 0.1, delta t is 0.1. Just reminding you of these things. Plus sorry, x1 was minus 0.9. X1 was minus 0.9. So then it comes plus 0.9 when you take the minus sign, which equals 1.1. F0 we already have from the previous step. In fact, this is the function at the beginning, which was just 1. That's when you put minus 1 into x and t is 0. So that means that x2 equals x1, which is minus 0.9, plus delta t on 2, which is 0.05, times 3 times f1, 3 times 1.1 minus 1. Right, so just plugging these numbers on the step, 3 times the function at f1, and then the function at 0, and that gives us x2. So x2 is 0.785. So you've got the idea. Once we have the function on the current step and the previous step, it's easy. We just wind it forward using those values on the step. So if we then iterate another 9 times, so that n equals 10, and t of n, which equals n delta t, is 10 times 0.1, which is 1, which is the point where we've got this nice true solution, e to the minus 1. We have the x value at step n is 10, is 0.3675. Is AB2. Let's just look back in the notes and see the results we had for, we'll leave forward Euler out because we know that was less accurate, but for RK2 we had x10 equals 0.3685. That was RK2, and we know that x star, true solution, is e to the minus 1, which is 0.3678. So actually AB2 is slightly closer in the 4th decimal place to the true solution. But the point is these are the same order of accuracy. Remember, Ford Euler was 0.34. Yeah, Ford Euler had x10 is 0.3487, way away from the true solution compared to AB2 and RK2. So these second order methods is confirming basically that AB2 has the same order of accuracy as RK2, but the way that accuracy is achieved is very different. It's achieved by using the function on the previous steps, whereas RK2 is achieved by multiple function evaluations within the time step. And both have advantages, both had disadvantages that I've discussed as we've gone forward. But that's quite nice that you can sort of see that in a very practical, almost very calculator type problem there. Okay. So that was Alan's Bashforth 2. And you may have noticed it's a little bit quicker to derive it than RK2. So I want to talk about two variants then on Adams-Bashforth, which gives us Adams-Bashforth 2. First one is, how do we achieve improvements, if you like, or on AB2. I mean, AB2 is quite useful and it's used a lot. Well, we could look at higher accuracy or order. We're going to look at that, which would be the AB3, and I'm just going to write that down. Or we could look at the AB2 is explicit. Remember, i.e. xm plus 1 is in terms of previous time steps. N and minus 1, minus 2. Well, in case of AB2, let's just leave n minus 2 out for the minute. That's more AB3. But we know from comparing forward Euler with implicit that explicit schemes can be unstable, can be numerically unstable. So we've got the higher accuracy of order, but then we got implicit version of AB3. And that gives what's called A Adams-Moulton. Okay, so that's what we're going to look as well, maybe in the next video. For the remainder of this video, I just want to show you the third order Adams-Bashforth method. So recall that AB2 was derived using a line or a straight line polynomial. If we use a quadratic instead, approx, we get a third order scheme. But now we require 3 points to define that quadratic, n minus 1 and n minus 2. So the trade-off with higher accuracy is that we've got to go further back in time, and because because we're defining a higher order polynomial, that requires more and more points. But that said, AB3 is still a very popular compromise because it gives that extra bit of accuracy. I'm not going to derive this, I'm just giving you the outline of how you go away and derive it. If you want to see, and it's right at the beginning, if you want to see how these higher order methods are derived, let's get. So there's this book, C. Karab Gunther. It's in the intro of lecture notes. If you want the reference, full reference, for full derivation. I'm pretty sure they have a full derivation on these higher order polynomials. Okay, so but we've, you know, everywhere in this course we try and basically it's about the principles underlying the methods. We're going beyond level 1. I hope you see that by now. But we're also not just trying to do really complicated derivations for the sake of it, but hopefully in the cases where we don't derive it, we just write down the what the steps would be to get that, so you understand where the method comes from. So with the third order then, it looks like this. So AB3, Adams-Bashforth 3, has this formula. So xn plus 1 again equals x of n plus delta t on 12 now, 23 f of n minus 16 f of n minus 1 plus 5 f of n minus 2. Okay, so the understandably the coefficients are getting more larger. We've got the delta t on 12. We've got a 5 there. Okay, and the key point is that now to get that third order accuracy, so this is, remember this is third order accuracy, to achieve that we're now going back step n minus 1 and step n minus 2, and basically you construct another figure again with those 3 points to construct a quadratic now that integrates forward in time. Okay, so that's completing for Adams-Bashforth. Our last ordinary differential equation time-stepping method is going to be Adams-Moulton method that I'll cover last time, which is this implicit version of the Adams-Bashforth scheme. And then final set of videos for week 5 will be on boundary value problems, which is a separate type of problem, but it's the other type of problem that is important. Normally you have either time stepping problems where you integrate forward in time. We've done a lot on that and we spend most time on that, but there are also boundary value problems in differential equations, and it's important we cover that a bit because they're the other main class of differential equations. Okay, so on that note, let's stop the video now. See you next time.